Yara, an in-depth theory of its role in malware detection and cybersecurity. 1. Introduction to Yara. Yara is a powerful, open-source tool used extensively in the field of malware research, threat intelligence, and digital forensics. Its main purpose is to help identify and classify malware through the use of textual and binary pattern matching. Developed by Victor Alvarez of VirusTotal, Yara was designed to assist analysts in writing descriptions of malware families based on textual or binary patterns. Theoretical foundations, Yara rules, signatures, and modules. Yara is fundamentally a pattern matching engine designed to detect malicious artifacts through a combination of string identification, logical conditions, and structured data interpretation. Its strength lies in how its core components, rules, signatures, and modules, interact to bridge human threat analysis with automated detection. Each component reflects a layer of abstraction, allowing human intelligence to be encoded in a machine-readable form. 1. Rules, the logic layer. 1.1 Rules as semantic filters. Yara rules represent the semantic expression of threat knowledge. They are crafted not merely to match bytes, but to contextualize meaning in the structure and behavior of digital objects. A well-crafted rule encapsulates the essence of a malware family, beyond superficial features. 1.2 Declarative nature. Rules are declarative rather than procedural. This means an analyst describes what to detect, not how to detect it. This abstraction allows security practitioners to focus on intent and indicators, while the engine handles the mechanics. 1.3 Cognitive reusability. Rules serve as a codified memory of investigations. Once written, they become reusable across cases, tools, and environments, creating continuity in organizational threat detection. 1.4 Hierarchical composition. Rules can be modular. One rule can import another using logical operators, e.g., include or import patterns, allowing layered detections, from narrow IOCs to broad TTPs, tactics, techniques, and procedures. 2. Signatures, the evidence layer. 2.1 Digital DNA. Signatures are the digital fingerprints embedded within rules. They are the granular artifacts, text, hex, regex, that uniquely characterize malware. While rules define the logic of detection, signatures encode the evidence. 2.2 Structural versus behavioral signatures. Structural, static patterns like hard-coded strings, PE headers, or byte sequences. Behavioral. Indirect indicators, such as command line syntax, environment variable references, or encoded APIs. This dual nature enables Yara to detect both static samples and dynamically altered variants. 2.3 Probabilistic signature design. While some signatures are exact, e.g., specific malware strings, others are probabilistic, designed to match families or classes of threats. This involves regex patterns that capture obfuscation, fuzzy byte sequences using wildcards, threshold conditions in the condition clause. 2.4 Signature entropy. Malware authors increasingly rely on polymorphism, packing, or encryption. Signatures can be designed to detect entropy levels, which are mathematical proxies for obfuscation or compression. 3. Modules, the contextual intelligence layer. 3.1 Augmenting rule capabilities. Modules act as interpreters of structured domains, PE headers, ELF metadata, hash algorithms, or sandbox behaviors. They enable Yara to understand format-specific structures without analysts writing complex parsers. 3.2 Enabling cross-domain correlation. Modules allow Yara rules to correlate string evidence with structural and behavioral contexts, such as detecting a string only in the .text section of a PE file, matching an API call pattern observed in a sandbox report, flagging files based on expired certificates in a PE signature. This correlation increases accuracy and reduces false positives. 3.3 Cognitive layering. Modules represent a higher abstraction tier in Yara's theory of operation. While signatures deal with bytes and strings, modules think in objects, functions, headers, sections, behaviors. This layering supports human-aligned reasoning, where analysts describe threats the way they analyze them, by behavior, structure, and function. 3.4 Extensibility and Custom Modules. Yara's architecture allows for custom module development, meaning organizations can build their own logic for proprietary file formats, in-house telemetry, or custom behavioral attributes. This flexibility cements Yara as a platform rather than a static tool. 4. Interplay between components. The real power of Yara lies not in individual components, but in their synergistic interaction. Rules orchestrate logic. Signatures provide the raw detection material. Modules enrich context and semantics. This tripartite structure allows Yara to scale vertically, from individual bytes to complex logic, and horizontally, across file types, data streams, memory, and behaviors. 5. Philosophical implication, Yara as a threat language. At its core, Yara is more than a detection tool, it is a language of threat expression. It allows security professionals to encode and share knowledge, transfer expertise across teams and generations, build institutional memory of adversary behaviors. By combining precise logic, encoded evidence, and contextual analysis, Yara provides a way to model digital threats in human-readable, machine-actionable terms. Yara in action, theoretical foundations of threat hunting and malware analysis. Yara is more than just a scanning tool, it's a semantic language for expressing digital threat intelligence. Its deployment in threat hunting and malware analysis reflects deep theoretical underpinnings that align detection science with adversary modeling, behavioral analytics, and intelligence-driven defense. 1. Yara as a declarative language for threat expression. At its core, Yara operates as a domain-specific declarative language. This means analysts don't write scripts or functions to detect threats, instead, they declare the traits and logic of what a threat looks like. This mirrors linguistic theory in artificial intelligence. Yara allows threats to be spoken through structured pattern descriptions. Form, the rule is the grammatical unit. Semantics, strings and conditions express meaning, i.e., what is malicious. Syntax, like a language, Yara has rules for structure, e.g., the strings. Section must precede condition. This structure makes Yara not only machine-readable but human-composable, allowing security analysts to communicate threat knowledge across teams and tools. 2. The role of Yara in threat hunting, a hypothesis-driven model. Threat hunting is the act of seeking adversaries before alerts occur. It is a proactive, intelligence-led approach to detection. In theory, it is based on hypothesis generation, formulating what a threat might look like and testing it against data. 2.1 Deductive reasoning in detection. Yara rules encapsulate deductive hypotheses. If malware X is present, then string Y and structure Z will be observable. This is equivalent to scientific theory, hypothesis experiment confirmation. For example, hypothesis, cobalt strike beacons use a specific configuration string. Yara rule, define the string, the location, e.g., memory offset, and a logic condition. Test, run Yara against memory dumps. 2.2 Intelligence integration. Threat hunters often translate threat intelligence, from reports, IOCs, TTPs, into Yara rules. This allows abstract threat data to become operational detection logic. 3. Theoretical function of Yara in malware analysis. Malware analysis is the process of understanding how a malicious sample works. Yara supports both static and dynamic analysis through theoretical constructs. 3.1 Signature theory. Yara uses pattern theory, a field of formal logic and machine learning, to match malware. These patterns, or signatures, reflect the ontology of malware families. A signature defines core identity, e.g., a byte pattern. Behavioral trait, e.g., strings like command exe/c. Metadata, e.g., compiler timestamp. This is analogous to biological taxonomy, where rules help classify species, families, strains, variants of malware. 3.2 Behavioral abstraction. In dynamic malware analysis, Yara can work with sandbox logs via Cuckoo module. This reflects symbolic reasoning, where behavior, e.g., API calls, mutex creation, is abstracted into logical patterns for matching. Yara, in this sense, becomes a behavioral modeling language. 4. Contextual reasoning through Yara modules. Modules provide Yara with contextual reasoning abilities. In theory, they extend semantic understanding of data formats, e.g., PE, ELF. Bridge structural knowledge with binary patterns. Enable domain-specific analytics, like examining certificates, sections, or file entropy. This reflects situated cognition theory in computer science. Yara doesn't just detect patterns, it understands where and why they exist within a structured system. 5. Detection precision, the theory of composability. Yara allows detection logic to be composed from reusable parts, rules referencing rules, string sets reused across families, conditions built from logical operators. This reflects modular logic, enhances scalability and maintainability. Set theory, use of quantifiers, any of, all of, number of. Maps directly to mathematical logic. For example, condition 2 of $malicious_string asterisk. This uses threshold logic, a concept used in probabilistic reasoning and fuzzy detection. 6. Cognitive and operational benefits, knowledge encoding. Yara encodes analyst intuition and experience into a form that machines can use. In theory, it acts as a knowledge representation framework for cybersecurity. Analysts use Yara to codify memory of past incidents. Teams share rules to create collective threat intelligence. Organizations store rules as part of their institutional knowledge base. This mirrors AI theory, where expert systems use codified rules to simulate human decision-making. 7. Advanced concepts, adversary emulation and TTP mapping. Yara rules can be designed around tactics, techniques, and procedures, TTPs, the behavioral blueprints of adversaries. This aligns Yara with the MITRE ATT and CK framework and Red Team methodology. 7.1 TTP-centric rule design. Instead of matching a malware hash, a Yara rule may match how the malware behaves, e.g., uses WMI to execute code. This reflects indirect detection, detecting intent and method, not just form. 7.2 Emulation detection. Red teams often use legitimate tools, e.g., PowerShell, MS Build, in malicious ways. Yara can be used to detect these tools' misuse patterns, helping defenders validate controls and visibility. 8. Limitations and theoretical trade-offs. Despite its power, Yara is bound by static scope. It cannot analyze runtime state unless extended by external tools. False positives/negatives, caused by overgeneralized or overly narrow rules. Evasion. Adversaries can adapt to known Yara rules using obfuscation and mutation. These limitations are common in all signature-based systems, reinforcing the need for adaptive, layered defenses. 9. Conclusion. Yara as a semiotic bridge. In theoretical terms, Yara is a semiotic tool. It links signs, patterns, with meanings, malware behaviors. Within specific contexts, files, memory, processes. Its value lies in its ability to represent threat knowledge with clarity and precision. Translate abstract intelligence into actionable logic. Augment human cognition with machine-speed analytics. By combining structured pattern matching with modular extensibility, Yara occupies a unique place in cybersecurity. It is both a microscope for reverse engineers and a radar for threat hunters. Building effective Yara rules, best practices, full theory. Yara is a rule-based pattern matching tool widely used for malware detection, classification, and threat hunting. While its technical function is to scan files and memory against predefined signatures, the real strength of Yara lies in its ability to encode human threat intelligence into machine-readable logic. Building effective Yara rules requires more than technical syntax. It demands an understanding of pattern recognition theory, adversarial evasion tactics, information entropy, and semantic modeling. This theoretical guide outlines the foundational principles and best practices for designing powerful, accurate, and resilient Yara rules. 1. The philosophy behind Yara rule design. At its core, Yara is a declarative language. Unlike procedural languages, which define how tasks are executed, declarative languages express what should be detected. Each Yara rule encapsulates a hypothesis about the presence of a particular threat or behavior, translating it into a structured form that a machine can evaluate. The process of crafting effective Yara rules mirrors the scientific method, hypothesizing that certain indicators signify malicious activity, then testing those indicators against real-world data. This positions Yara rules as not just detection artifacts, but as formalized threat models. 2. Characteristics of an effective Yara rule. An effective Yara rule adheres to several theoretical qualities. Accuracy. It identifies the intended target without matching unrelated or benign files. Precision. It uses distinguishing characteristics that are unique to the threat. Resilience. It is robust against obfuscation, minor mutations, and code variations. Efficiency. It operates within resource constraints and does not slow down scanning. Clarity. It is readable and understandable by other analysts, supporting collaboration and long-term maintenance. These properties reflect well-established principles in information theory, software engineering, and data science. 3. Semantic structure of Yara rules. A Yara rule is composed of components that together express a detection logic. Each component serves a theoretical purpose. Metadata encodes contextual information about the rule, such as who wrote it, what it targets, and its source. This supports traceability and knowledge sharing. String definitions represent the observable indicators of compromise, signatures, file contents, or malicious patterns. These reflect pattern recognition and signal processing concepts. Condition logic defines the rule's decision-making criteria using Boolean logic. This portion is directly aligned with formal logic and set theory. Together, these parts enable Yara to act as a semantic bridge between human threat knowledge and machine-scale execution. 4. Theory of string selection and pattern matching. One of the most critical aspects of rule creation is the selection of strings or patterns that represent the malware. This process is governed by several theoretical considerations. Information entropy. Unique or rare strings carry higher entropy and are less likely to appear in benign files, making them ideal candidates for detection. Noise reduction. Common strings, like system messages or generic code, introduce noise and increase false positives. Theoretical detection models prioritize signal-to-noise optimization. Obfuscation awareness. Adversaries frequently use string obfuscation techniques, e.g., encoding, encryption. Effective rule writers anticipate such tactics and apply fuzzy matching principles through pattern abstraction. In practice, this means selecting indicators that are both specific enough to isolate a threat and general enough to detect variants. 5. Logical design in detection conditions. The rules condition section is its logical engine. This portion of the rule expresses under what circumstances the defined strings or characteristics constitute a match. The design of this logic is rooted in predicate logic and probabilistic inference. Theoretical best practices include use of quantifiers, logical quantifiers, like any of or all of, model threshold-based detection, which aligns with theories in probability and statistics. Combining multiple features, relying on multiple, diverse indicators reduces the risk of false positives and increases detection robustness, akin to ensemble modeling in machine learning. Contextual constraints, logical conditions that factor in the location, structure, or metadata of the file enable semantic filtering, an approach grounded in situated cognition theory. 6. Performance and efficiency theories. Effective YARA rules are not just about detection, they must also be resource conscious. In enterprise environments where millions of files are scanned, efficiency is paramount. The theoretical underpinnings here relate to computational complexity and algorithmic optimization. Strategies to maintain performance include minimizing unnecessary string evaluations by applying early file type filters, reducing scope using file size or offset conditions to exclude irrelevant data, using selective modules to ensure rules are only applied to appropriate contexts, e.g., only to executable files. These practices embody principles from runtime analysis and decision tree pruning, commonly found in algorithm design. 7. Evasion resistance and rule robustness. Malware authors constantly adapt, using polymorphism, encryption, and code morphing to evade static detection. YARA rules must be designed with adversarial adaptation in mind. The theoretical response is based on redundancy theory. Using multiple indicators for a single threat increases the likelihood of detection even if some indicators are altered. Behavioral anchoring. Instead of focusing solely on static strings, effective rules attempt to detect behavioral traits, which are harder to obfuscate and more persistent across variants. Detection generalization. The balance between specificity, to reduce false positives, and generalization, to capture more threats, is guided by bias variance trade-off theory. 8. Maintainability and collaborative intelligence. The sustainability of a rule is just as important as its initial detection capability. Over time, malware evolves, teams change, and new data becomes available. Effective rules follow the principles of collaborative knowledge management. Version control and clear metadata support rule auditing and lifecycle management. Human-readable logic facilitates teamwork and shared understanding. Modular structure allows for reuse and inheritance of common logic across multiple rules. This approach transforms YARA rules into knowledge artifacts, part of a broader organizational memory. 9. Conclusion: YARA rule writing as a cybersecurity discipline. Building effective YARA rules is not merely a technical task, it is a strategic practice grounded in multiple theoretical domains. It draws from logic, pattern theory, behavioral modeling, and threat intelligence. The best YARA rules are conceptually sound, theoretically valid, operationally effective, functionally accurate, tactically useful, adaptable and shareable, cognitively accessible, readable and maintainable. When crafted thoughtfully, YARA rules empower analysts to transform fleeting threat intelligence into enduring detection logic, bridging the gap between adversarial behavior and defensive response. Integrating YARA with security tools, a practical guide. YARA is a powerful pattern matching tool extensively used in malware research and threat detection. However, its true potential is unlocked when integrated into broader security infrastructures, enabling automated, scalable, and contextual threat detection across enterprise environments. This guide explores the theoretical foundations, benefits, and strategic considerations of integrating YARA with various security tools. 1. The role of integration in modern cybersecurity. In modern cybersecurity, no single tool functions effectively in isolation. Security tools form part of a layered defense ecosystem, where data, alerts, and detection capabilities must be seamlessly shared to provide comprehensive visibility and rapid response. Integrating YARA into this ecosystem transforms it from a standalone detection script into a dynamic, context-aware component that automates malware detection across different environments, enriches alerts with detailed forensic context, enables real-time or near-real-time response actions. The integration aligns with the cyber kill chain model and security orchestration, automation, and response (SOAR) principles, enhancing both detection depth and operational efficiency. 2. Types of security tools for YARA integration. Understanding the variety of tools where YARA can be embedded is essential. Each offers unique opportunities and challenges for integration. 2.1 Endpoint Detection and Response (EDR). EDR platforms collect endpoint telemetry and provide real-time detection and response capabilities. Integrating YARA allows for scanning files and memory on endpoints using YARA rules. Automated quarantine or alert generation when matches occur. Behavioral correlation combining YARA hits with other endpoint events. Theoretically, this enhances defense in depth by extending signature detection to the endpoint layer, where malware often executes. 2. Security Information and Event Management, SIEM. SIEM systems aggregate logs and alerts from across the network. YARA integration can enrich SIEM data by feeding YARA detection results as part of event logs, correlating YARA detections with network or application events, triggering automated workflows or threat hunting based on YARA matches. This leverages data fusion theory, combining heterogeneous sources to improve situational awareness. 2.3 Network Security Tools. YARA can be integrated with intrusion detection/prevention systems, IDS/IPS, or network forensic tools to scan network traffic captures for malicious payloads matching YARA signatures, detect malware delivery or lateral movement attempts in real time. This application is rooted in network behavior analysis, extending YARA's static file scanning to dynamic network content inspection. 2.4 Threat Intelligence Platforms, TIPS. TIPS aggregate and curate threat intelligence feeds. Integrating YARA allows organizations to share YARA rule sets as threat indicators, automate updating and distribution of detection logic, correlate YARA detection data with external intelligence for context. This supports collective defense and intelligence-driven security operations. 2.5 Malware Sandboxes. Malware analysis platforms can use YARA to automatically tag and classify samples based on rule matches, prioritize analysis queues according to YARA detections, generate enriched reports linking behavioral and signature-based findings. This exemplifies the triangulation approach in threat analysis, combining multiple data points for robust classification. 3. Conceptual benefits of integration. Integrating YARA with other tools unlocks several strategic advantages. Automation, manual analysis is reduced as detection is embedded in operational workflows. Scalability, YARA scanning can be distributed across large environments without sacrificing performance. Contextualization. Correlating YARA results with telemetry and external intelligence creates richer insights. Proactive defense, early detection at endpoints and network layers reduces dwell time and damage. Operational efficiency, security teams can focus on high-value investigations instead of repetitive scanning tasks. 4. Theoretical considerations for effective integration. When planning integration, several theoretical factors must be considered. 4.1 Data interoperability and formats. YARA output must be translated into formats compatible with target tools, e.g., JSON, XML, syslog. Designing flexible data transformation pipelines adheres to information theory and systems interoperability frameworks. 4.2 Real-time versus batch processing. Integration strategies must decide between real-time scanning, immediate detection and response but with higher resource demand. Batch scanning, periodic analysis with lower overhead but potential detection delays. This trade-off reflects principles of real-time systems theory and queuing theory. 4.3 Rule management and update synchronization. Maintaining consistency of YARA rule sets across integrated tools requires centralized rule repositories, version control and automated distribution, validation pipelines to prevent conflicting or erroneous rules. This is informed by software configuration management and distributed systems theory. What is YARA? YARA, yet another recursive acronym, is an open-source tool used to identify and classify malware samples through pattern matching. It allows analysts to write descriptions, rules, that characterize malware families based on strings, text, binary, regex, file structure, headers, sections, sizes. Opcode patterns and behavior. Core components of Yara rules. Each Yara rule has the following structure. Rule name. Meta. Description equals describes the malware or condition. Strings. $A equals malicious string. $B equals 6A406800300000 / hex pattern. Condition. Any of them. Sections. Meta, descriptive tags, author, description, reference. Strings, specific indicators, text, binary, regex. Condition, logical expression determining a match. How Yara is used in practice. 1. Malware classification. Identify new samples that belong to a known malware family. Cluster samples into known campaigns or threat actor tool sets. 2. Threat hunting. Scan memory or disk on live systems for artifacts of malware. Run on CM collected data or EDR telemetry. 3. Incident response. Detect presence of malware on endpoints post-breach. Scope infection and track lateral movement. 4. Reverse engineering. During analysis, strings and behaviors observed are codified into Yara rules. These rules can be used to match similar malware. 5. Automated detection. Integrated into tools like VirusTotal, Cuckoo Sandbox, The Hive, and custom EDRs. Used for continuous scanning of incoming files or memory dumps. Types of matching. File-based, scan entire files or directories for matches. In memory, analyze running processes or memory dumps. Network-based, some modified versions of Yara are used in deep packet inspection, DPI, contexts. Best practices in writing rules. Balance precision versus recall, too loose equals false positives, too tight equals missed detections. Use wildcards and regex sparingly for performance. Version and comment your rules for maintainability. Test against goodware, benign files, to reduce false positives. Yara in the cybersecurity ecosystem. Yara is often part of a broader ecosystem. Integrated with MISP for threat intelligence sharing. Coupled with sandboxing tools like Cuckoo. Automated via orchestration platforms like the Hive or SOAR tools. Used with VirusTotal intelligence for retro-hunting samples. Advantages. Highly customizable and human-readable. Open source with a large community. Integrates with many forensic and security tools. Limitations. Needs manual crafting and expertise. Can be evaded by advanced obfuscation or packing. Performance intensive if poorly written. 1. Malware analysis at FireEye, now Trellix. Scenario: FireEye uses Yara to detect variants of Advanced Persistent Threat, APT, malware in large-scale campaigns. Implementation. Analysts create Yara rules based on malware signatures and behavior observed during reverse engineering. These rules are deployed in FireEye's sandbox environment and endpoint agents. Impact. Enabled early detection of evolving APT malware like APT28 and FIN7. Helped proactively block new variants before signature-based antivirus tools were updated. 2. Threat hunting at Microsoft Security Response Center, MSRC. Scenario: Microsoft uses Yara to proactively hunt for malware in their massive cloud and enterprise environments. Implementation. Custom Yara rules are run on telemetry and memory dumps across Windows Defender ADP and Azure Sentinel. They focus on code patterns, strings, and metadata. Impact. Caught in-memory malware missed by traditional scans. Detected fileless attacks in 0 days during early exploitation stages. 3. Incident response at a Fortune 500 financial institution. Scenario: after detecting suspicious behavior, the IR team needed to quickly scope the infection across endpoints. Implementation. Used Yara rules to scan endpoint memory and file systems for malware traits. Focused on string and binary patterns from forensic analysis. Impact. Contained the breach within 24 hours. Avoided regulatory penalties by demonstrating rapid response and containment. 4. Custom rule sharing via MISP, malware information sharing platform. Scenario: multiple certs and SOCs use YARA rules to share threat intelligence. Implementation. YARA rules are shared as part of MISP event indicators. Integrated with tools like the Hive and Cortex for automated scanning. Impact. Improved cross-organization detection of shared threats. Accelerated response time across national certs in the EU and APAC. 5. Reverse engineering and signature development at Kaspersky Lab. Scenario: Kaspersky analysts reverse engineer malware samples and generate YARA rules for new threat families. Implementation. YARA is used in their internal tooling to cluster and categorize new malware. Rules are refined to avoid false positives and published for public and commercial use. Impact. Contributed to global visibility on campaigns like Duku, Stuxnet variants, and Equation Group. Supported defensive research and public reports. 1. YARA as a detection language. YARA is more than just a tool, it's a domain-specific language, DSL, for expressing patterns of malicious code. In this light, analysts use YARA to encode their understanding of malware families. Detection engineers use it to convert reverse-engineered findings into proactive scanning tools. Threat researchers use it to track actor-specific toolsets over time. YARA rules become a bridge between human analysis and machine enforcement. 2. YARA in the cyber kill chain. YARA can be applied at different stages of the cyber kill chain, by Lockheed Martin. Stage YARA usage. Reconnaissance rare, but some threat intel rules can detect prep tools. Weaponization detect malware builders or packed payloads. Delivery email attachment scanning, URL patterns. Exploitation memory scanning for exploit artifacts. Installation detect dropped files or persistence mechanisms. C2, command and control, signature of beaconing DLLs or C2 infrastructure. Actions on objectives toolset detection, e.g., Mimikatz, Rubius, Cobalt Strike. 3. YARA as a forensic instrument. In post-compromise investigations. Disk forensics, scan acquired disk images or artifacts. Memory forensics, use tools like volatility or recall with YARA rules to identify in-memory implants, hooks, or injected code. Triage, rapidly sort through large volumes of data to prioritize analyst focus. This positions YARA as a scalable filter in forensic pipelines. 4. YARA in CI/CD for threat detection. Modern detection engineering teams adopt DevOps-style pipelines for detection development. YARA is used in version-controlled repositories, e.g., GitHub. Automated testing pipelines. Rules are tested for accuracy, false positives, and performance. Deployment pipelines, automatically pushed to EDR/XDR or CM platforms. This treats detection like code, a living, versioned product. 5. YARA in cross-vendor threat sharing. YARA serves as a common language across CERTs and ISACs, information sharing and analysis centers. Public repositories, e.g., GitHub, Malware Bazaar. Threat intelligence platforms, MISP, OpenCTI. It helps normalize the dissemination of IOCs and TTPs in a structured, automatable form, far more actionable than prose reports. 6. YARA as an intelligence gathering tool. In advanced environments, analysts use retro-hunting, scanning historical malware repositories, like Virus Total Intelligence or PolySwarm, using YARA rules to identify the first appearance of a new threat. Track changes in malware evolution. Pivot on code reuse or unique strings. This shifts YARA from a reactive to a proactive research tool. 7. YARA in malware attribution. Sometimes, a specific byte sequence, compiler artifact, or hard-coded string can link malware samples to threat actors. YARA rules help Detect shared codebases, e.g., Lazarus group samples. Track actor-specific cryptography libraries or packers. Identify developer habits like naming conventions or junk code. One, Yara and the theory of signature-based detection. At its core, Yara operates on signature-based detection, which is rooted in pattern recognition theory. A signature in this context is a distinctive pattern, strings, bytecode, or structural features that can uniquely or probabilistically identify malicious artifacts. Theoretical strengths: deterministic and explainable. Efficient at runtime with limited false positives, if well written. Limitations: susceptible to evasion by obfuscation, encryption, polymorphism. Requires constant updates as threats evolve. Yara extends traditional antivirus-style signatures with flexible logic and context, making it more powerful in hands of experts. 2. Declarative rule-based language design. Yara is a declarative language, meaning the rule writer declares what to detect, not how the system should search for it. This is fundamentally different from procedural detection logic, e.g., Python scripts. It offers separation of logic from implementation, readability and maintainability, reusability across platforms, memory, files, sandboxes. Yara's rule engine is essentially a logic interpreter for file and memory analysis. 3. Yara in the context of formal language theory. Interestingly, Yara rules share features with regular languages in formal computation. You define a set of acceptable strings or conditions. The Yara engine works like a finite automaton, checking if the input, a file, memory dump, etc., belongs to the set. This makes Yara theoretically decidable. You can always compute whether a match occurs, and it will always terminate. 4. Yara versus heuristic and behavioral detection. Heuristic detection uses rules of thumb, e.g., runs from temp folder. Statistical properties, e.g., file entropy. Behavioral detection watches actions over time. Network connections. File creation. Registry edits. Yara is static and syntactic. Operates on binary level indicators. Doesn't observe behavior unless integrated with a dynamic tool, e.g., sandbox. Trade-offs. Yara is faster, safer, doesn't run malware. Behavior-based detection is richer but more resource-intensive. They are complementary, not mutually exclusive. 5. Epistemological perspective, Yara as codified knowledge. From a knowledge theory standpoint, each Yara rule encodes a unit of expert knowledge about how a threat presents. Yara becomes a knowledge base, not just a tool. It represents an organization's collective memory of threats. As new threats emerge, analysts extend the rule base, much like a semantic graph of known adversary techniques. 6. Yara and detection as code, DAC. Detection as code is a modern philosophy where detection logic is treated like software code, managed with version control, testing, CI/CD. Yara fits perfectly into this model. It is written in a structured syntax. Supports modularity and reuse, e.g., rule imports, includes. Can be lint, tested, and deployed automatically. This turns detection from an art into a disciplined engineering process. 7. Symbolic representation of threats. Yara allows symbolic abstraction. $A equals P at SSW0RD is a literal signature. $B equals /AZZ 6 \D 2 / is a pattern abstraction. Conditions like any of $A** and file size less than 1 MB are symbolic representations of threat logic. This abstraction allows analysts to generalize from one sample to a whole malware family. Why Yara matters in theory. Yara thrives because it blends Computational theory, finite automata, regular expressions. Knowledge representation, codifying adversary behavior. Software engineering principles, modularity, declarativity. Cyber defense philosophy, precision, transparency, control. It represents a human-machine partnership in the ongoing effort to understand and defend against malicious code. 8. Yara and formal logic, propositional reasoning. Each Yara rule can be seen as a propositional logic statement. If $A or $B and not $C then match is a compound logical condition. Rules combine Boolean expressions and predicates over observable features, strings, sizes, counts. In this view, strings are propositions, string X is present. Conditions are logical statements, any of them, all of them, not in this order. This positions Yara as a domain-specific logic engine, similar to expert systems. 9. Yara and information theory, entropy and signal. Malware detection through Yara can be seen as an application of signal detection. The malware is a signal buried in the noise, normal software, benign files. Yara rules are tuned to identify high information patterns, that is, patterns that occur more often in malware and rarely in clean files. Information theory concepts. Entropy, malware often has high entropy, e.g., encrypted sections. Yara can match based on that. Shannon's concept of surprise, the more rare or specific a string is, the more useful it is in detection. 10. Yara and threat modeling, mapping to TTPs. Yara rules often target tactics, techniques, and procedures, TTPs, defined by frameworks like MITRE ATT and CK. Tactic, Y persistence, lateral movement. Technique, how DLL injection, scheduled tasks. Procedure, what a specific malware's implementation. Yara captures the observable artifacts of these procedures, strings, binary patterns, file layout, etc. This allows defenders to operationalize threat intelligence, turning abstract TTPs into concrete detections. 11. Yara and cognitive load theory. From a human-computer interaction, HCI, and cognitive science lens. Yara reduces cognitive load by giving analysts a consistent, expressive syntax to externalize complex pattern logic. Helps chunk knowledge. Instead of remembering how a malware behaves, the analyst encodes it in a rule. Enables collaborative memory. Teams can reuse and share rules, building a collective understanding of threats. Yara thus serves as a cognitive offloading tool in threat analysis. 12. Yara as a semiotic system. From a semiotics, study of signs and symbols, perspective. Yara rules act as symbolic representations of adversary behavior. Each string or pattern is a sign referring to a concept, e.g., invoke Mimikatz points to credential dumping. The full rule becomes a narrative of what the malware is, how it behaves, and what to watch for. This makes Yara a semantic bridge between code and meaning, vital in malware research and threat intel. 13. Yara and adversarial thinking. Yara development is a classic example of adversarial mindset. If I were an attacker, how would I try to evade this rule? Analysts must anticipate evasion strategies, obfuscation, string slicing, dynamic loading. This cat and mouse dynamic drives better abstraction in rule writing. Constant refinement and adaptation. Use of defense in depth, Yara plus heuristics plus behavior. 14. Yara and the philosophy of security. Philosophically, Yara embodies several core tenets of security. Transparency. Unlike black box AI detectors, Yara is human-readable. Accountability. Rules are authored by people, errors are traceable. Control. Defenders choose what and how to detect, not dictated by vendors or opaque models. Composability. Rules can be modular, reusable, and integrated into layered defenses. It represents a human-centric model of trust and control, aligned with open source and defensive transparency ideals. 15. Yara as a tool of defensive epistemology. Finally, consider Yara as part of a defensive epistemology, the science of how we know what we know in cyber defense. A detection is not true in an absolute sense, it's probabilistic evidence based on encoded knowledge. Yara formalizes evidence-gathering logic. It becomes part of an epistemic chain: observation, hypothesis, rule, testing, confirmation, match. This positions Yara as a methodological instrument in building trust in our conclusions about malicious activity. 16. Yara and automata theory. Yara rules effectively define regular languages, sets of strings that satisfy certain patterns. The matching engine can be modeled as a finite state machine, FSM. Each string is a state transition. Boolean conditions are decision nodes. File or memory inputs are streams processed against these finite rules. Thus, Yara can be seen as a language recognizer, a computational model that accepts or rejects inputs based on pattern conformance. 17. Yara and the theory of computability. Yara operates within the bounds of decidable computation. For every input, file or memory, Yara rules always produce an answer, match/no match. The rule language avoids Turing completeness to ensure termination, avoiding infinite loops or runtime unpredictability. This places Yara in the class of safe, verifiable tools, unlike more dynamic or behavioral tools that may have non-deterministic outputs or rely on simulated execution. 18. Yara and detection grammars. From a computational linguistics perspective, a set of Yara rules forms a grammar, a formal system of tokens, structures, and rules for generating a language of threats. Terminals, strings or patterns, e.g., evil.exe. Non-terminals, metarules or includes, e.g., import PE. Productions, combinations of strings and conditions. Syntax, conditions and logic define the grammar structure. This allows defenders to speak about malware in structured, parsable ways, similar to domain-specific knowledge representation. 19. Yara and Bayesian reasoning. Yara rules are deterministic, but in theory they could be extended into Bayesian threat detection systems. Each string match could be treated as evidence supporting a hypothesis, e.g., this file is emotet. Bayesian inference could be used to weigh partial matches, improving detection where obfuscation hides part of the signature. While Yara doesn't natively support probabilistic reasoning, it can be embedded into systems that do. 20. Yara in socio-technical systems. Cybersecurity is a socio-technical system, a blend of human, organizational, and machine elements. Yara rules are shaped by human bias, institutional priorities, and collaborative practices. The rules reflect not just malware traits, but analyst assumptions, team strategies, and industry trends. Studying Yara adoption is thus a window into cybersecurity culture, how we encode trust, authority, and interpretation into technical artifacts.